Hey everyone! Today we'll be walking through question 4 on the week 8 worksheet. This question is called 2-3 forever, and we'll be looking at how to insert into a 2-3 tree, as well as how to convert a 2-3 tree to an LLRB. Before we jump into the first section of this problem, I do want to take some time to go over what a 2-3 tree is and why we use them. If you're already familiar with this, feel free to skip over this part and just jump into my explanation of 4.1. But without further ado, let's get started. So why do we use 2-3 trees? I guess the best way to explain this is to start by looking at a binary search tree. In the best case, a binary search tree can be, you can find any node in log n time. And so a tree that satisfies this case would look more like this. As we can see, this tree is balanced, and as a result, it's bushy. And what we mean by bushy is that it has a pretty even number of nodes on either side of the tree, on the left and the right side of the tree. And so this allows us to actually narrow down our possibilities by half every time we want to basically isolate and find a specific node within the tree. And so that's why we can get a single node in log n runtime. In the worst case, however, finding a node within a BST can be a log, or not a log n, it can be a theta n runtime. And so this is because a BST can also look like this. Here we can see that this is a spindly tree, so it's not balanced. And we call this spindly. It looks more like a linked list than a tree, actually. And the reason for why this happens is because you can actually have one node and only insert greater elements. And we can actually end up with a structure like this, where finding this element would require iterating through every single element in this tree. And that's why we have a theta n runtime in the worst case of finding a single element in a BST. And so this is kind of why we use 2-3 trees. 2-3 trees will help us always balance our trees. So our trees will always be balanced and bushy, which is what we want because we want to have a better runtime. Basically, we're trying to get that log n runtime at all times. And so what a 2-3 tree looks like is if in a traditional BST, we have basically one root node and each root node can have 2 children. In a 2-3 tree, we can have up to two elements in one node, and each node can have 3 children. So each node can have 3 children with either 2 elements in one node or 1 element in a node. Either way is fine, but this is a valid 2-3 tree. And essentially what this does is it allows us to balance our trees more conveniently by ensuring that we are basically not going down the spindly path where we have just a chain of nodes connected to each other. And we'll see how this works as we do 4.1. So yeah, let's get started with 4.1, which is draw what the 2-3 tree would look like after inserting 18, 12, and 13. Cool, so I'm actually going to copy over this tree so that we can start this on a fresh page. So let's paste it here. Cool, so we have this tree. We want to insert 18, 12, and 13. 12, and 13. So first I'm going to insert 18. Looking at this tree, I know that it follows the same kind of left side has to be smaller than the root and right side has to be greater than the root. It's very similar to a BST in that way, so it follows the same conventions. And so I see that 18 is bigger than 8, it's bigger than 14, and it actually should be to the right of 15 and 16. And so the way I insert into a 2-3 tree is that I'm actually going to overstuff the node. So here I'm going to redraw this. The right side, or the left side, sorry, is unchanged. But on the right side, I have 14, 10. And I'm actually going to overstuff this node. So let me show you where I'm inserting it, just in red. So I actually have 3 elements in this node, and this is not valid. This is not a proper 2-3 tree. You can only have a maximum of 2 elements in one node. But the reason why I'm doing this is because 2-3 trees are special in that the way they balance themselves is that you overstuff a node, like so, and you can actually push the middle node up to the previous level. So here I have 15, 16, and 18. I'm going to actually push the 16 up to this previous level and add it on after the 14. So my tree is actually going to look like this now. The side is unchanged. 3 and 7. On this side, I have 14 and 16 together, and then I have 10, then 15, and 18. And so this is a perfectly valid 2-3 tree because it has a node with 2 elements in it, which is fine, and that 2-element node also has 3 children, which is fine. And it also works out because on the left of 14, we have 10, which is smaller. Between 14 and 16, we have 15, and to the right of 16, we have 18, which is greater. So this is a valid 2-3 tree. Cool. So let's add on the next element, which is 12. So when we're looking at this, we need to see where 12 fits in our tree. And so I'm looking at it, 12 is greater than 8, so it would be to the right of 8. It is less than 14, so we know that it should be somewhere on the left of 14. And we know that it's greater than 10, so it should probably be to the right of 10. And so from that, I can probably figure out that I should put it to the right of 10, and I can add it to that element. So it has to that node, so that it has 2 elements in that node. So redrawing this tree, again, the left side is unchanged. And then on the right side, I have 14, 16, 10, and I'm adding 12. And this is a perfectly valid thing to do since there's only 2 elements in that node. And then I have 15, and then I have 18. Cool, so that worked out. The next thing I want to do, so I've done 18, I've done 12. The last element that I want to insert is 13. And so now when I look at this, I want to see where 13 could go. So I see that it should be to the right of 8. It should be to the left of 14. So it needs to be in basically this node. And it should be to the right of 12 because it's greater than 12. Cool. So now I can draw this out. Cool. 14, 16 should be unchanged so far. Here we see that since it's to the right of 12, we're actually overstuffing that node again, which is okay, but it's not a valid 2-3 tree, so we'll need to balance it again. And we'll see that how that happens. I'm going to do this in red since it's actually not allowed right now, but we're going to need to do this just so that we can draw it out properly. Then we have our, sorry, let's change this color to black, our 15, and then our 18. Cool. So now I'm going to break this up. I'm going to send 12 up to the previous level. And so that means to the left of 14. And we'll see something interesting happen there. So let's actually just draw this out. 8, 6, 3, 7, unchanged as usual. Then here, what we're doing is we're actually sending 12 up. And when I do that, I actually make another 3-element node, which is also invalid. But we're going to do that just so that we can continue in our balancing process. And so even if you think it's going to be invalid, I would urge you to just do it and then try to balance it after you do that. So I'm moving 12 up, 14, 16. I'm overstuffing this node. And then here, I'm actually just going to do this all in red because it's going to have 4 children now. So to the left of 12 will be 10. Between 12 and 14, I'm going to put the 13. Between 14 and 16, there'll be a 15. And to the right, that would be 18. So we see this is actually like 3 elements in this node, and there's 4 children, which is actually not allowed in a 2-3 tree. So we're going to need to balance further. The way we can do that is since we have 3 elements in this node, we're going to actually push this 14 up to the previous level. And so I'm going to actually draw this out again. And when we do that, things will balance themselves out. So when I move the 14 up to the 8 level, I'm going to have 8 and 14 on one node. To the left is the same. So 6, 3, and 7. Then we can see here that we're actually going to have a middle section which contains these nodes, so 12, and then to the left is 10, to the right is 13, and then to the right of this we're going to have this section, which is 16, 15, and 18. And so that gives us a valid 2-3 tree, perfectly balanced, and we can see it's bushy, and that's what we wanted. So yeah, we've successfully added those 3 elements. Cool. And so the next part of this question basically tells us to convert this resulting 2-3 tree to a left-leaning red-black tree. And so just before I jump into this part, I do want to give you guys a little bit of background on why we do this. So the reason why we want to convert a 2-3 tree to LLRBs usually is because 2-3 trees are actually really difficult to represent in code. It's pretty hard to kind of simulate the fact that you're having 3 elements in one node and then, or not 3, sorry, 2 elements in one node and then 3 children. That's pretty complicated. And so what an LLRB does is it basically looks exactly like a BST. So it still has just like 2 children for one node, but we can denote that 2 elements are in the same node by adding this red link. And so by doing this, we are making it easy to code, but also representing the same balanced bushy structure that was in a 2-3 tree. So it's basically the best of both worlds. And we'll see a little bit more about how this linking is done when we convert this 2-3 tree to an LRRB. So if we go down here, we have this finalized 2-3 tree, and we want to convert it to an LLRB. And so the reason why it's left leaning is simply because whenever you have 2 elements in one node, so for example, this has 2 elements in one node, you're going to actually push the left element down. And so there's no other reason for it other than it's an L left leaning tree. And that's just how they told us to do it. So here we're going to have 14 in one node. So this is looks like a normal BST, and that's why we can't have 2 elements in one node, but we're going to represent the fact that 8 and 14 are together by adding a colored link between them. So I'm going to push this 8 down to the left side, and I'm going to add this colored red link there. And so this indicates that 8 and 14 are in the same node, but it allows it to have the same structure as a normal BST. Cool. And then the rest of the tree will follow pretty easily from here. So it's going to be 6 on this side, and then 3 and 7. So that structure has not changed. And then on the right side of this 8, we're going to have 12, 10, and 13. So 12, 10, and 13. And then on the right side of this 14, we're going to have 16, 15, and 18. So we see that this basically looks like a BSD still, but we're able to use this red link, this color, to indicate that it's like the structure of 2 elements in one node. And so yeah, that's why we use LLRBs, because they allow us to have bushy and balanced trees that are easier to represent in code. If you have any questions about anything I did today, make sure to reach out to your mentors. And as always, just try to practice more of these problems if you're struggling. The best way to kind of see how this balancing works is to try it out yourself on a couple problems. And yeah, reach out if you have questions. Cool. That's all for today.